Okay, so this is section 10.3. We're now going to get into our polar coordinates portion of this chapter. Really, polar coordinates are kind of just an extension of parametrics, and hopefully you'll see what I mean when we get to it. But the general idea behind polar coordinates is that it's just another way of getting to certain points in space. Um, so if you think about how you've done things in the past, we've always done things on the Cartesian coordinate plane, or what people call the rectangular coordinate plane, because we use X and Y values. So you typically go like to the right or to the left, and X amount of spaces, up and down, Y amount of spaces. And you can get there by either going right and then up, or up and then right, or however the directions are. And it forms kind of a rectangular idea. And if you remember, your rectangular grids, they're basically just a lot of boxes, and you can plot points that way. Polar coordinates are very similar in the fact that we're going to plot points in space, but now instead we're actually going to use concentric circles. I'll explain more about that when we get to the second page. For right now, I kind of want to go through a little bit about how we do this using your calculator, because it is going to be important for some of these things to use the calculator. Some of these polar graphs can be quite tedious to try and figure out what they are and what they look like without actually using the calculator. Not that it can't be done, but we're not really going to do things that way too much. So the first thing you want to do is, let me go ahead and see if I can pull up my calculator here. I know I've got it down here somewhere. There it is. Okay, so the first thing you want to do is you want to go to, well, you want to turn it on, but you want to go to the mode, because we want to change our mode. So the mode is right up next to the blue second button right there. And what you should see on your calculator might look slightly different, but for the most part, it should look similar. You should see that normally the FUNC, the fourth one down, is function. That's your typical y equals function. Then you've got PAR, which we haven't really dealt with. That's the parametric function, which you can input stuff into, and that would have been good for the prior two sections if you wanted to just see what the graphs look like. But the one we're going to use specifically, we're going to scroll down, and we're going to put this in polar mode. Okay. Then you want to go ahead and have your table set start at 0 and make your increments pi 12. So how do we do that? If you look along the top row in the blue, you see the TBLSET right next, it's right above the window button. So you'd have to push second because it's in blue, table set. And right now mine starts at 0 already. I think that's the default, so it should. And it says we want to make our increments, or our change in our table, pi 12ths. So let's scroll down here. We'll make it pi 12ths. Enter. All right. Then you can go to the table, plot points. Notice that it says here, notice that the table is going to give you theta values first. So second graph will give you the table, and it gives theta values there. Okay, and then we'll also give us our R values once we actually input something. So we've gone ahead and changed the mode and everything to what we needed to. So I'm going to push second mode and quit, get out of this. All right, so now what we're going to do is we are going to graph the given polar functions using the graphing calculator. And then we're just going to sketch them right here. So the first one is R equals sine of theta. Oops. I'm going to just put a nice little grid here. I'm going to do the same thing over here. Now we're going to go back to the calculator. Here we go. And we're going to go to y equals. But you'll notice instead of y equals, it says r equals, and that's good because everything's going to be in terms of r and theta when we talk about polar mode. Again, I'll explain all that much more in detail on the next page. So I'm just going to input sine of theta. And notice that when you push your xt theta n button, it's now going to be theta because we're in polar mode. So it's automatically switched that for us. And then we're going to push zoom 6. Now I always push zoom 6. That gives me a standard 10 by 10 window. Problem is that doesn't really do a whole heck of a lot for us because this is in polar mode. That would be really nice if it was in rectangular. Doesn't really look very good, to be honest with you. So I'm going to go back to zoom, and what you should notice is that you have number 7, which is a trig function. So let's push 7 for trig, and now it looks much better. Now hopefully you can tell that's a circle. Let's zoom in because you're going to need to know all these different features to be able to see these things better. So I'm going to go to zoom, and in is number 2. And notice it didn't do anything. It's because you have to push enter after you push zoom 2. And there you go. You got a nice, what looks to be a circle, and that's all that it is. It's a circle, oops, which sits on top of the x-axis. And that was completely awful. So I am actually going to cheat because I can. And I'm going to give us a circle which sits on top of the x-axis, just like that. And that's what it looks like. Now think about this. This is r equals sine of theta. Sine of theta is positive in the first and second quadrants, which is why the whole thing sits up on top of the x-axis, because this is the angles and everything for sine are positive in the first and second quadrants. Again, I'll explain much more about how this works on the next page. Now let's go back and graph r equals cosine of 2 theta. So now you have to notice that what we have is a double angle. So let's go back to our y equals screen. We're going to get rid of that one, clear it out, and we're going to do cosine of 2 theta. And now it's already in the zoomed in mode and all that kind of stuff. So I'm just going to push graph and see what it gives us. That actually worked out quite nicely. All right, it's a pretty neat little design. What this is called a 4-petaled rose. There's actually a reason that they call it a rose, because it doesn't really look like a rose, but there is a reason for that. Let's go back up to here. Oh, so anyway, you can kind of see what it looks like. All the petals are symmetric to the x and the y axis. So I'm going to sketch that. This one I actually am going to sketch. I'm not going to try and cheat or anything on this one. I'm not probably going to sketch it in the same order that it went on the calculator. That is definitely not the best, but you get the idea. Not the best sketch. What happened down here? Somehow I inserted another circle. Not that that's a big deal. It doesn't matter that that's there. All right. So again, there's a couple of things, and if you've learned all this stuff before, that's great. If not, that's okay. It's not, we don't have to memorize it right now, although the more you know it, the better and easier these things will be. Because the angle of cosine is doubled, or is an even, I should say, angle. Instead of 2, it could be 4, it could be 6, it could be whatever. As long as it's an even angle, what you will have is double the amount of petals that your angle is in here. Now, if that was a 3 theta or a 5 theta or a 7 theta, it would actually be exactly the same number of petals as that angle. But when it's an even number like that, it doubles the amount of petals. There's also stuff that goes on with the symmetry. With cosine, it's symmetric to the x-axis. With sine, it's symmetric to the y-axis. Again, not all something that we have to necessarily memorize, but it is good to know if you happen to know these things. All right, the far more interesting thing is on the next page. So this actually explains a little bit about how polar works. So notice what we're going to graph here is r equals 2 cosine of theta, not cosine of 2 theta like we just did. It's 2 times the cosine of theta. So what we're going to do over here is we're going to create, I'm going to write that down just above here, just to make sure I can scroll down a little bit better. What you can see, this is a polar graph. It is not a rectangular graph because each one of the segments in there is not a rectangle. It's close, but it's slightly different. The way a polar graph is measured, it is measured in terms of r, which is a radius, and theta, which is an angle. So you're basically going to have the origin, which we're used to having right at the center. that would typically be the origin of an XY axis right in the center. We actually call this the pole, like the North Pole, the South Pole, whatever. That's the center when it comes to polar coordinates. From there, you're going to measure a certain distance from the pole, called the radius, how far out it goes, and then the angle that is created with the positive x-axis. That is going to be how you actually measure your coordinates. So, for example, if I wanted to do, let's just say, by the way, each one of these circles, which are called concentric circles, they are called concentric circles because they are circles which stem from or originate from a certain given point called the pole, and they are all equally distant apart. We're going to call each one of these circles a distance of 1/2. So out to here is a half, out to here is 1, out to there is a 1.5, and so on. Just going to make it easier to graph and see what's going on. Let's create a chart for r equals 2 cosine of theta. So over here, I'm going to put our angle, and then on this side, draw a line all the way down there as best as we can, I'm going to put r for our radius. So given certain angles, we're going to be able to get a radius. So basically your theta in this case is like your independent variable, your x. R is like your y, it's your dependent variable here. So let's do what makes sense. Let's just start off with a nice easy theta angle of 0. We'll put a 0 there. Well, if theta is 0, now you do have to know your trig values here pretty well. Cosine of 0 is 1, so the 2 times the 1 gives me 2. And then we'll go with the ones, again, that kind of make sense. Let's just go around our unit circle. Let's go with pi over 6. Cosine of pi over 6 is root 3 over 2 times the 2 out in front is just going to give us root 3. And then the next one we would estimate, and not estimate, the next one we would use would be pi fourths. Cosine of pi fourths is root 2 over 2 times the 2 out in the front is just going to give me root 2. And then pi thirds. Pi thirds, cosine of pi thirds is a half. A half times 2 is 1. And then pi halves, and we will have at least completed one quadrant of cosine. Cosine of pi halves is 0, so 2 times 0 is 0. All right, we're going to go with one more full quadrant. We're going to go into the second quadrant of angles, which should be 2 pi thirds, 3 pi over 4, and 5 pi over 6, finishing it off with pi. All right, so let's figure out those values. 2 pi thirds should be the same thing as pi thirds, but it's now in the second quadrant, so it's negative. So we'll get -1. And then 3 pi fourths, again, second quadrant, so that should give us negative root 2. Second quadrant, 5 pi 6 should give us negative root 3. And then cosine of pi is -1 times 2 gives us -2. All right, so now let's go back up, and we're actually going to graph what we have here so we can see what's actually happening. All right, so when our angle is 0, angle of 0 is, again, with the positive x-axis. Angle of 0 means we didn't go anywhere. A radius of 2 means from the origin we're going to go out 2 units. Remember, each one of those circles we're counting as a half. So out to this one is 1, and then out to this one is 2. So that's our first point. At an angle of pi over 6. Now we're going to have to figure out where the angle of pi over 6 actually is on here. Pi over 4 is actually the easier one because that is the angle, which is 45 degrees right through here. I'm going to erase that in a second. That's your 45-degree angle right there. So pi over 6 is actually going to be the solid blue line that comes from the origin out this way. Pi over 3 is going to be this one. So hopefully that will help you when it comes time to graph these. So I'm going to erase those because we don't need that there. So pi over 6 is going to be the first solid blue line that goes all the way from the origin out. Well, it's going to be a distance of root 3. Now we're going to have to use some approximation. Root 3 is approximately 1.7. That is very good for us to know, just for purposes of estimation. And just so we get it, root 2 is approximately 1.4. And these are just good approximations to use. So if I go to pi 6, I want to go out a distance of 1.7. Well, remember, each one of these concentric circles is a half. So half, 1, 1.5. 1.7 is not quite halfway, but the bigger you make the dot, the more it's going to look like that. So that looks like that's probably about 1.7. All right. Pi fourths is going to be 1.4. So that's going to be just less than the third concentric circle, right on that middle, which is going to be, let's see, 1.4, right about there, just less than that one. And then the easier one is going to be at pi thirds. It'll be a distance of 1, so that's 2 concentric circles out. And then the last one at pi halves, the one we're straight up and down, well, I have no distance, so we're right back to the origin. So we're right there. All right, now let's explain what's happening with the next ones. 2 pi thirds. An angle of 2 pi thirds is actually going to be off of that line right there. But the radius is negative 1/2. And the question is how you have a negative it's a negative 1. How do you have a negative 1 radius? That doesn't make any sense. A radius is a distance. How do you have that? Well, the negative actually just indicates a direction. Okay, it's not actually a negative value for a radius, it's a direction. So 2 pi thirds is the way the arrow was that I just pointed, but a negative 1 radius means I go in the opposite direction 1 unit. So that actually means I'm going to go this way 1 unit, which gives me a point right there. So that's what a negative radius means. You go to the angle, but then you go in the opposite direction from the pole. So again, I'm going to erase this and this piece right here. So 3 pi over 4 would normally be here, but we're going to go the opposite direction because it's a negative and it's root 2, so that's about 1.4. So that's going to be 1, 2, almost, but not quite 3 concentric circles. And hopefully you can see the symmetry that is happening with the ones on top. All right, 5 pi over 6 would be a negative root 3, which is going to be 1, 2, 3, just a little bit, almost not, but not quite halfway in between the third and fourth. And then the last one at pi, if I go out that direction, that's pi, but I need to go negative 2, so it's backwards 2 units. Well, that puts me right back where we started from, right there. And what's going to happen is the more and more I go around the circle, this is just going to trace over itself. So what you should see, if I kind of sketch through this, is that this is supposed to create a circle. If my drawing was a little bit better, that's what it would look like. That's a circle. So that is how you would sketch one of these things by hand. Okay, not something that I am ever going to actually have you guys do. You will not have to sketch these by hand, but this is how they are created. So negative angles mean go the opposite direction from the original angle, and all of the angles are created from the positive x-axis, and the radius itself is the distance from the pole. So that's how coordinates are done in polar coordinates. They are going to be in the form of r, whoops, what the heck happened there? Of r theta. Okay, those are going to be your polar coordinates. Instead of xy, it's r theta. All right, we spent plenty enough time on that. We will come back and do all the examples in one video. The examples will not take very long.